so let's start on the what we left last time. I hope you guys keep watching the videos on YouTube channel. So make sure you guys follow up all the lecture videos. So even though you don't come to the lecture, you can still follow the lead in the lecture. So, but last time we talked about the chemical equations. Okay, so chapter 3 is about how you're gonna do with the chemical equations. So the chemical equation is a certain made of certain sections of the chemical compounds and status and numbers and plus and minus sign and so forth. So you're going to have some the compounds and the molecules on the left side, and you have some yield sign. Okay, so they're always going left to the right, always going to the left to the right. And you're going to have some other different compounds or molecule will be on the right side. Okay, so the this will be obviously some chemical formulas that you're gonna see on the chemical equations. You're gonna have a plus sign, meaning we just kind of mix them together. Okay, we kind of interact. We're gonna put them in the reaction together to make the two different products here. So the one on this side, you're gonna see the products. So C and D is the products, okay? And A and B is your reactants. Okay? So this is your starting material that you're gonna start with in the chemical reaction. So this plus sign in here in the reactant side, meaning they're going to interact each other. Okay? The product side, they meaning just they're separate, just they're not doing any interaction here. So at this point, when you get the product, that's the end of the chemical reaction. There's nothing happening anymore on the right side. They're just indicating two separate products. That's only means in the plus sign. And on the here, it means they're going to interact each other. That's what it means. Okay. And then one couple more things is that you're gonna have a little bit of small subscribe in the down right bottom corner of the each. It means that this compound or this compound and on what physical state of that now in that position in the chemical reactions and after. So you can say if we put Z over here, it means it's gas phase, gas molecules. Okay. If we put L, means it's a liquid. Okay. If I put S, it means a solid. Okay. So you'll be able to know what it really means in the ones in the small parentheses at the right bottom corner of your chemical formula you see on left and right of chemical equations. Make sense so far? Good. Okay, perfect. That's great. Just one more thing. I didn't mention last time. You'll see this one sometime soon too. It's the AQ. This is just aqueous. Aqua means water, but aqueous means it's adjective form of the aqua. The meaning it is surrounded by water molecule. Meaning it's a dissolving water. Okay, so that's why it's surrounded by water. So if there's like a salt or other compound to be dissolved in water, they have to be surrounded by water molecule, so they can be fully dissolved in water. And then we can put AQ instead, meaning they're just aqueous condition, meaning they're surrounded by water molecule, meaning they dissolve in water. Okay? So anyway, those are the ones that you're gonna see on here. And then there's some numbers on the front of it for each reactants in the product. We call them coefficient or coefficient numbers. So this will actually tell you about how many of each reactants, and this will make how many of products of C and D in each of the product here. So this is where we're gonna use in the chemical reaction that we're gonna use stoichiometry. So stoichiometry means simply analysis on how many of each reactants will make how many of each product, and we're gonna do it by numbers. So this is why we need the coefficient number for each. So we'll be able to know, oh, we need to have this many of A and B to make this many of C and D. Okay, so this is what we call stoichiometry, and this is why we did the one example was combustion reaction of the organic compounds. Okay, so let's try to do a quick review on the combustion reaction again. So combustion reaction is the one we can try with this stoichiometry analysis. So combustion reaction, it simply means something is burning, meaning it gives a lot of heat energy to the outside. Also, they're combining into oxygen. The later you're gonna learn why when they bond to the oxygen, they'll give a lot of energy. And when we hit the enthalpy change and also like quantum numbers. But before then, we know as in the the experience, combustion means burning. Something is burning. So for example, we can burn some organic compounds. So if you guys remember this, organic compound is simply the compound that mainly made of carbon and hydrogen. Okay. So I gave you one simple example last time. It was methane. But it's just one carbon and it's just the 4 other surrounding hydrogen atom. Okay, because carbon is group 4 element, so we should have a 4 max possible bonding to the 4 different hydrogen. So this might be the simplest form of the organic compound. So anyway, so if you do the combustion reaction, literally we'll interact with the oxygen. So we'll create a lot of energy and also in form of heat. So the outcome of those two is simply carbon dioxide and water. So once again, if you try to get this information, like I said, when you do the stoichiometry analysis, you need to know how many each will make how many of carbon dioxide and water. That's the thing we need to solve. So we're gonna fill out those coefficient numbers so we know more about this reaction in more completed chemical reaction equation. So the easiest way, like I told you before in the Monday lecture, you can always start with 1 with your organic compound, because the organic compound is the only source you can see the numbers of carbon and hydrogen on the left side. So basically what we're gonna do is we try to match the same numbers of each element, which is carbon, hydrogen, oxygen, on the left, on the right, the same. Because if you guys remember this in the first part of chapter 2 was about the mass conservation rule and the proportion rule, meaning any one of the carbon and hydrogen oxygen cannot be just disappear or appear during the chemical reaction. It has to be all equal on the left to the right. Nothing will be either missing or just pops up from nowhere. No. This has to be all equal amount, left and the right. Okay. So this is why we try to match up the same number for each element on the left and right. So if we start with the number 1 over here, that gives at minimum we have 1 carbon and 4 hydrogen, because each methane has 1 carbon but 4 hydrogen. So even though you put 1 over here, it doesn't mean that you're going to have only 1 hydrogen but 4. It makes sense, right? Because that's 4 hydrogen. So that means minimum you have 1 carbon. So I'm gonna put 1 over here because each carbon dioxide has only 1 carbon. So maybe I can just put 1 here. But for hydrogen, each water molecule has 2 hydrogen. But to make 4, I'm gonna put 2. So you can have 4 hydrogen on the right side as well. Okay. So now we're happy with the 1 carbon, 4 hydrogen as well on the other side. It's 1 carbon, 4 hydrogen on this side too. Now we're gonna balance the numbers of the oxygen, which is 2. Because if you look at the carbon dioxide, it has already 2 in 1 carbon dioxide molecule. So even though you put 1 over here, it doesn't mean you only have 1 oxygen, but actually 2. Because the 1 carbon dioxide will have 2 oxygen, so 2. But the water has only 1, because it is H2O. So each water molecule only has 1 oxygen, but there'll be 2, so there'll be 2. So in total, you have 4 oxygen on the right side, the product side. So to make the same 4 oxygen on this side, you have to put 2, because the oxygen is one of the diatomic molecule, meaning there has to be 1 molecule will carry 2 atoms. So it'll be 2 times 2 will be also 4 oxygen here. Then you're done. So now you know how many methane, how many oxygen gas molecule will interact. That is 1 and 2. And then they will make 1 carbon dioxide and 2 water. So it's stoichiometry is done. Because we know how many will interact, how many products. This is what we did on Monday. Okay, makes sense, right? Good. Perfect. Right. So yeah, this is a basic setup for chemical equations, just using one example. So that was combustion reaction. There's another type of a reaction I want to show you is what we call combination. Combination reaction. Combination reaction simply means you have like A plus B. Just gonna arrow here. We'll make AB. Okay? Meaning 2 separate reactants will combine, literally combine to make 1 product. Okay? So this is slightly different from combustion reaction, right? The combustion reaction will be making a lot of heat energy outside, but also will make some oxide and other elements as well. It doesn't really have to be 1. But the combination is the one that actually combines together, so it can make only 1 product. So we literally combining 2 reactants into 1. So we call this, it's slightly different from combustion reaction, we call this combination reaction. So I can give you one example, is this one. Nitrogen gas is also diatomic molecule, so it'll be not just N, but N2, okay? N2. And the hydrogen here also is the diatomic molecule, so it's not just H, but H2, okay? So if we try to combine these two, we try to put the combination reaction over here, they're going to make ammonia, okay? Over here, okay, ammonia. So the if that is the case, are we done here? Do you look at the number here? What does an add up? What's that? Perfect, coefficient numbers. We need to, so for now, we have some idea how, like, what what compounds will make what compounds, but we need to know how many now. How many now? So we still need to do stoichiometry. So here's the thing. Let's try to start with the 1 over here, okay? 1. Okay. So then we can try to with the 1. And then you can try to start with the 1 over here. That means at minimum, how many nitrogen you have on this side? 2, right? Because each nitrogen gas molecule will have 2 nitrogen atoms in it. Okay? So that's why each ammonia has only 1 nitrogen in here. So even though you put 1 here, it has to be at minimum 2. So that makes 2 nitrogen here as well. Because each ammonia will have only 1 nitrogen. So if it makes the minimum 2 nitrogen on this side, to do the same, you have to put not 1 but 2. Okay? So in that case, if you have a 2 ammonia, that makes 6 hydrogen on this side. Because each ammonia has only 1 nitrogen but 3 hydrogen. So if you have a 2 ammonia at minimum, you have to have a minimum, you have to have at least 6 hydrogen on right side. Right? Okay? So to make the 6 hydrogen on this side, what number should be here if each hydrogen gas molecule carry 2? 3, perfect. Perfect. That's great. Okay. Kind of makes sense, right? Perfect. All right. There is an easier one. Maybe you can have some carbons in the solid, and you can interact this one with some oxygen gas molecule. Okay. So maybe you can have some carbon dioxide over here. Is it done? Yes, it's done already. Because it's just one. 1, 1, 1. So if that is the case, you see only 1 is required, not 2 or 3. You don't have to put the number there, it's okay. You can also put the 1 there. but you don't have to. If it's just the one, it's already done right there. Because it gives us the same numbers of the carbon, oxygen already there with 1, 1, 1. Okay? Alrighty. Okay, makes sense, right? Can I move on? Okay, perfect. You guys doing great. Alright, so if that is the case, you're thinking about, can it go the other side? Yes, we can. We call this decomposition reaction. So it's literally going backward. So we're actually going the AB now making A plus B. So now they're breaking apart as a separate compound. So maybe I can give you one example here. It will be the copper 2 hydroxide here. Okay. So if you have this one, they can move on to copper oxide and water. Okay? If that is the case, actually there's I'm sorry. There's something I want to tell you here. Actually, I should have told you already, but you see this copper over here, right? And this is OH. So copper is the 2 plus over here, and OH is 1 minus. So this is a good example of also the ionic compounds too. But when I call this compounds, I just call this not just copper. This is name of this one is hydroxide. This is hydrogen and oxygen, so oxide. This is hydroxide anion. This is a copper cation. In that case, it's ionic compound, right? So in that case, I'm just gonna copper hydroxide. That will be actually slightly wrong because this is addition to what we discussed before. Do you see where the copper is? Could you find the copper on the periodic table? So copper is actually, sorry for you looking at this, but copper is right there. So if you look at the copper, is in the down in the middle. We call this D block, okay? D block. So if you have any metals in the D block, we call them transition metal. Transition metal. So copper is also transition metal. Okay. So if this transition metal is, do you guys remember this? If you look at the ones in the transition metal, we skip that one for the grouping in the groups, right? 1, 2, 3, 4, 5, 6, 7, 8. But we just skip that part, right? There's a reason why. So if there is some metals in the transition metal, like D block, they don't have one specific form of charge. So we cannot group it. There's no use. So meaning copper can be 2 plus, but sometimes copper can be 1 plus. If you just look at it, if you just name this one copper hydroxide, people will not know if it's just the one copper 1 plus hydroxide or copper 2 plus hydroxide. They don't know because the copper can do both way. Does it make sense? So in this case, we know the formal charge of the copper by looking at the formula, which because the hydroxide anion usually only carry 1 minus, okay? But there's a 2, right? So that makes 1 neutral ionic compound, meaning by looking at the chemical formula, oh, I know what charge should be on the copper now. It's not 1 plus, but has to be 2 plus. If it was 1 plus, you should see only 1 hydroxide there, because hydroxide is -1. But there's 2 because it was interacting with the copper 2 plus to make it neutral. Makes sense, right? So when we name this one, whatever the metal in the D block in your periodic table, in the transition metal box, you name copper and 2. We normally put the numbers in Roman number. So not just 2, but just Roman number 2 and hydroxide. So this is kind of something you can remember for naming ionic compounds. You can just name the ionic compounds what it says on the cation part, anion part with IDE, which is the hydroxide here. But if you find the metal cation in the D block, just make sure you look at the numbers of the anion part and what charge, or tell you what charge it should carry on the other transition metal cation. So that makes the copper 2 hydroxide. So if we have this one, it's copper 1 hydroxide. Make sense, right? Okay. So just a quick, I'll do this again because I calculated all the dates in the calendar. You know, we have an exam on the mid-February, right? So I think we can have a lot of time for the review session anyway. So we'll go over this one again. Okay. Anyway, so in this case, as you can see, this is the carbon 2 hydroxide here, and they need to break apart in and another products here. So they kind of separated from the one reactants here. So one reactants make the two products. It's a good example of decomposition here. So this will become just simply one copper 2 oxide, and then this is water here. So this is the good example of decomposition. So the one reactants breaking apart into two products is decomposition. If you have two reactants combined together to make one product, is combination. So it's kind of a opposite way to work. Does it make sense? Okay. Sort of. Okay. So let's do one more. Okay. Let's do one more. So if you have calcium carbonate, so the calcium carbonate is if you look at the calcium in the periodic table, it's in the group 2. So you know calcium is 2 plus for sure. It's unlike the ones in the transition metal, it's a set, because we know it's in group 2. It should have 2 plus charge. Okay? And that makes this carbonate, this is also another example of polyatomic anion that has -2. Because you see there's one calcium, one carbonate anion, makes a one ionic compound, that we know the calcium has 2 plus, this carbonate should have -2. That is indeed right, the carbonate carries a -2 charge. So that's why when it gives one calcium, one carbonate, makes the one ionic compound formula over there. Okay. So if that is the case, calcium oxide plus carbon dioxide over here. Okay. So in this case, also you have a one calcium carbonate, right? But it breaking into two products, which is the one is the calcium oxide, the other one is carbon dioxide. So that is also a good example of decomposition reaction. You see the difference, right? Combination difference. I'll move on. Okay. So that's pretty much all the reaction, either combustion, combination, or decomposition. We're gonna learn a bit more in detail later with the displacement reaction too. For now, it's pretty good. Okay. So the next one is the formula weight. Okay. So if you look at the chemical formula, you know how many of each element are making that certain compounds together. Okay, so when you look at this numbers of elements in the one chemical formula, you'll be able to get the numbers for the formula weight. Because the formula weight simply means the sum of each atomic mass and compounds. So I'll give you some example here. This is H2SO4. Can you guys actually? This is a quick review. If you can remember, do you know what's the name of this one? So this is a sulfate. This is the one that has AT name. So we call this sulfate. Then there's a hydrogen there. So will be Oh, that's close. When you do the hydro something, meaning is when it's only one. the binary. So binary means hydrogen and the halogen, hydrogen and one element too. So we want one. But this is a polyatomic anion, so you don't have to do hydro. Yeah, so we just.
It's going to be sulfuric acid.
Perfect. Perfect. That's absolutely right. So in this case, you don't have to do hydro, but just this is a sulfate. This is a sulfate. Nice. Very nice. And we just change this ATE to IC acid. And then we're gonna just call this sulfuric acid here. So the name of this one is sulfuric. So that makes, if that is SO3, that'll be, so you put perfect. Sulfurous, yes, perfect. If it's even less, hypo up per, but that's the perfect. That's great. So I will actually give you a good table, some study guide, that which compound will be commonly used in chemistry, and also what the polyatomic anion will have an AT name, so you can actually learn about this one more in the uniform way. But anyway, so you can start with this one. So if you have H2SO4, simply it kind of makes sense what is written in the chemical formula. Each sulfuric acid will have a 2 hydrogen, and they have a 1 sulfur, and it has a 4 oxygen here. Okay. So only thing you have to do is that the periodic table will be given on your exam, so you don't have to memorize anything. But if you look at the numbers written right under your chemical element symbol, you see the numbers in red, right? You see like 1 and 4 and so on. So if just find that numbers, that is your atomic mass number, and then just copy it here and multiply by how many you have in each compound. So there's 2 hydrogen. So I'll just make a easy like a whole number. Just make it just make the calculation easier. So this is the about 1, right? 1 point something, right? 1.0 something. So 2 times 1, okay, plus, I think sulfur is 32 something, so I'll just make it 32. So 1 times 32, okay? And then you have a 4 oxygen, 4. Oxygen is about 50.999 something, with just 16. Make it, yeah, I'll make it easier. So in this case, if we just make it 2, oh, it's good. 2 plus 32 plus, this will be 64. Thank you. So if you add them all, it will be 2 plus 32, 64. That makes 8 and, okay. So you can have some number over here, okay? That is your formula weight. Once again, you can also say AMU, or you can say gram per mole. It's okay. We haven't got to the Avogadro number yet. I only explained once, I think very briefly in the first week of the school, but either you can say AMU or gram per mole is okay. So you can have a number for the formula weight if you know what's the chemical formula for the compounds. Okay. So maybe we can try. Oh yeah. Can you guys try this one? I'll give you this. This is not extra credit yet, but maybe you can try this one. Okay. By the way, what might be the name for this one? Just quick review. This is the metal. This is not metal. This is ionic compounds, and this is group 2, right? So it'll be, you don't have to worry about the number and anything. So it'll be just calcium chloride. Perfect. This. It's not going to be calcium dichloride because calcium is metal. Okay. You don't have to do that when it's metal. So calcium chloride over here. Can you guys get the formula weight for calcium chloride? It's really quick. So look at, so calcium is about 40. Chlorine is about 35.45. But you know, you can always make it easy. But the numbers all says over there. Okay. Actually, I cannot see the number. Can you guys see the numbers? Really? Oh, I'm old. Oh my, really? So this is yeah, I think calcium is 40. You can make it easier, 40. And this is 35.45. You just need to count how many calcium, how many chlorine in one ionic compounds, And that's pretty much it. Okay. And just add the number. Okay. 1 calcium, 2 chlorine. So just 1 times 40 plus 2 times 35.45. That would be your formula weight. Right? Maybe, yeah. So it'll be 110 point something. Okay, good. Perfect. Okay, perfect. So if you got number somewhere around 110 point something, that is perfect. Okay. So this is how we do the formula, the weight. Okay. Makes sense, right? Can I move on? Okay, perfect. Let's move on. Okay. So this is the time that I'll show you another one. But I hope you guys not very confused on this one. We have a formula weight. We also have a molecular weight. So if it's confusing you, you can almost formula weight and molecular weight are similar concept, but only slightly different. So we made a molecular mass or molecular weight, usually for the organic compounds that usually make a chemical bond with the covalent bond. Okay. So the NaCl here, which is the chemically bond, but in the name of ionic bonds, because this is simply what interaction between cation and anion. Given because of the loss of electron or gain of electron. So that shows the potential difference that makes the very kind of common sense make electrical like an interaction by the Coulomb's law. So this is a different type of chemical bonds than covalent bonds. And this type of thing, if that is made in the ionic bond, we don't consider them as a distinctive regular molecular bonds, but you can still call this in one type of chemical bonds. So to be make it much easier to understand, if you feel like you see the very obvious ionic compounds, just make sure you use this formula way for good, just making sure that you're getting all terminology right. If it's all organic compounds or any compound that only made in a covalent bond, you are also free to use the molecular weight as well. But to be honest, I don't know why this is so important here to make it formula and molecular weight, because this is my opinion. Don't list for as a chemist, I think ionic bond is also chemical bond, and it could be possibly only slightly different from the covalent bond. Later on, you're gonna learn about the electronegativity. Not today, but the electronegativity simply means how strong each element can pull the electron to themselves. So usually it's very high on the right top corner of the periodic table, except the last column. So the fluorine is the one that is the strongest. Okay, so if that is so much difference between two different elements, that element with very strong electronegativity and very weak electronegativity makes really clear separation of the numbers of electron in here to another. So that makes really good ionic bonds. And also, if it's not so clear, like we have a common ground to share, we just call it covalent bond. If it's somewhere between, we call this polar covalent bonds. And we actually made one distinction by using the Pauling unit numbers. We're gonna learn it actually sometime later. So the bottom line is not so always clear. Like if you look at the hydrofluoric acid, I'll give it next time. It's just but for your exam, this is how it works. If it's covalent bond, it's free for you to use molecular weight. But if it's ionic compounds, you rather just use a formula weight instead of molecular weight. Okay. If you use molecular weight, I would say, that's not really perfect, but I wouldn't blame. But still, for your exam or another general term of the science, stick to the covalent bond, molecular weight, ionic bond, formula weight, and as well. Okay. I hope that makes sense. I don't want to confuse you, but this is what they do in chemistry. I think it's not really necessary, but this is the rule you need to follow. So anyway, so molecular weight. So one example once again. So maybe it can give you, I hope you guys remember this one. So if you have 4 carbons in the carbon chain, okay, because we know they'll be saturated by hydrogen, and each carbon will have a 4 single bond. So 4. This is why carbons are joined to hydrogen, because they already have a carbon to the right and the left, the other carbons and these 2. But in the terminal carbons will have a 3, because there is no carbon making bond to it. So there'll be 3, 2, 3. Okay. So that makes the 4 carbon, 10 hydrogen over there. Okay. So in that case, it's just pretty much the same. So this is all covalently bonded, right? So then just 4 times carbon plus 10 times hydrogen. That makes really good molecular weight. So once again, the carbon is actually 12.008. I'm just going to use 12. Okay. And same for the hydrogen, it will be just 1 for me. Okay. And then 4 times this 12 will be 48. Plus 10 times 1 is obviously 10. So there will be 58 gram per mole. Or you can say AMU. Either way, it's fine by me. Okay. So this is just slightly different term, but very similar to what we just did with the chemical formula. We just wanted to distinguish them from what bond they're making and their elements in the compound. Okay, ionic compound and molecular compounds. It's pretty easy, right? Can you guys try? You still have 5 minutes, right?
Can you do one where how it was like a single bond between all the carbon, one with the double?
Yeah, okay. So I can show you. Let's try the double bond then. So, but how about we try this one? Okay. So this is 3 carbons, right? So it'd be prop. But we have a double bond here, right? So we put not A and E, but E and E. There's a propene. Okay. And then double bond count as 2, right? Not 1. So this carbon will only have a 2 hydrogen on it. And this is 1, 2, 3. So there's only 1 hydrogen here. This one is 1, 2, 3, 4. Okay. So technically it's all 4 actually. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So that makes 3 carbons, but only 6 hydrogen, not 8. Okay. So can you guys do the molecular weight for this one real quick? The 3 carbons and 6 hydrogen. So you only need to do is triple the carbon atomic number. Atomic mass, and 6 times the hydrogen atomic mass, and just add them all. Okay. Real quick. Real quick.
42.
Yay! 42. You guys see this one, right? 12 times 3 plus 1 times 6 will be 42. Okay. All right. The next part is the percent composition. So this is what we call percent composition. There's a hidden words after this one, but they don't normally show. But this means actually biomass. So percent composition biomass. I mean, it's normally you don't say in the textbook, but it actually says what it means. So biomass means, for example, if you have a methane over here, right? You're actually going to get you can say formula a molecular weight here. This is 1 carbon, so it'll be 1 times 12 plus, and this is what? 1 times 4, so it'll be 4. Okay? So that makes 16 AMU, or 16 gram per mole. Okay? And here, so you know the whole molecular weight, or formula weight, you can say 16 gram per mole over here. And I want to know carbon percent composition by mass. Meaning, this is the carbon, this is the hydrogen, right? You just copy this one to here. That is 12. Okay? And you just multiply the fraction number by 100%. So you can have a numbers in percent by mass. So if you do this, this would be 3/4, right? So
Simplify it?
yeah, if you just divide by 4, it's a 3/4, right? Yeah. So that's well, I can say methane shows 75% carbon by mass. Okay. So I'll promise you, I'll do this again on Friday. So I'll stop here.